So the whole math review is this is a bunch of stuff that came out of your multivariable calculus class that you've probably forgotten because you don't use it incredibly often. It's not hard, and this is the basic math you need for dealing with thermodynamics. So what we deal with in thermodynamics are state functions. Our state functions have this form. You have some function of a set of our independent variables is equal to a constant. If you have a function that is equal to a constant on the right side, and you have a set of variables, you can then express that constant and the infinitesimal changes of each of those variables in terms of partial derivatives. So for example, the change in x is going to be the partial of x with respect to y holding z constant dy plus the partial of x with respect to z holding y constant dx. And you can do that for all of the variables. And this is how we're going to be taking our state functions, most notably Gibbs free energies, and expressing them in terms of the independent physical variables that we have. We have some other useful expressions that you can use. Again, this is just mathematical manipulation. In your textbook, there's a whole chapter on dealing with, I think they call it auxiliary functions. And if you look at the homework problems, all the homework problems are, do you remember these? So one of them is that, switch to red here, so up. One of them is that you can take, two of these partials with respect to the same thermodynamic variable, and they equal to 1. In terms of bad engineering math or physics math, you can think of it as, well, the z's cancel, the x cancel, and goes to 1. It's a little more complicated than that, but those of us in the physical sciences have been known to successfully use bad math to build skyscrapers and then whatnot, go to the moon. It works well. The other implication is that then you can take this, and if you flip it, you get z over x, x over z raised to the minus 1. We also have this triple product rule that if you have these 3 partials, they're equal to minus 1, and then you can go about using these manipulations in order to move, for example, this over to the other side, right? So now instead of dy by dz, it's now dz by dy, and the negative 1 stays. And you can also get these ratios to come out, and there's lots of other things you can do. So that is the level of complexity of math we're going to be doing in this class. A lot of us just sitting down with a piece of paper and pencil and screwing around with the variables until you get what you want. So the implications of this, though, for us, is that we were talking about state functions, and we said that, well, we can take, we were talking about ideal gases, right? Because those are kind of nice systems, again, not particularly useful for materials engineers. We are much more interested in solids, but they're handy for us to work with because it's a small number of variables. And the implications for us is that we have some function of pressure, volume, temperature, and it's equal to 0, which is a constant, which means that all of these rules hold, and we can do things, for example, write dV is equal to the partial of volume with respect to pressure at constant temperature, dP plus the partial of volume with respect to temperature at constant pressure, dt. So we can now break down our variables in terms of these differential equations, and it also implies that we can take integrals. So we can integrate, take the left side from v1 to v2, and then integrate the right side. So this is for a transition, say, state 1 with v1, p1, t1 to to state 2, B2, P2, T2. So integrate this from P1 to P2, and this from T1 to T2. This left-hand side then is equal to B2 minus B1, which is equal to delta B. So this means that we now have an expression for the change in volume as we move from state 1 to state 2. And what's also important is that these variables, the temperature and the pressure, they're independent of each other. So this expression implies half independence. And we had that picture we drew before, where we just kind of reasoned through this. We had temperature, pressure, volume, and I said that this volume then is going to be some surface, and it's a single value surface. So for a given temperature and pressure, you can only have one volume. R surface. And at some point, you've got a pressure, you've got a temperature. If you change, well, you've got another state here. And you could have taken multiple paths. It doesn't really matter. The only thing that matters is where you sit on that surface. So this is the application of state functions. So talking about this expression, we could say, well, this is really great. The math tells us a bunch. But it does more than that. And the reason it does more is that these mathematical terms have physical meaning. I'm talking about, for example, change in volume with respect to pressure at constant temperature. And what does it mean if you have, a solid, you change the pressure, or a gas, you change the pressure, you keep the temperature constant? Well, that is equal to beta, which is the isothermal compressibility. Likewise, the change in volume with respect to temperature at constant pressure on alpha, and that is the isobaric thermal expansivity. Oh, wait, sorry. Made a mistake there. One mistake here. Let me draw an arrow here, because that's not exactly right. There's a scaling factor here. So beta is equal to minus 1 over volume dV dP constant temperature. Alpha is equal to 1 over volume dV by dT. Sorry about that. So what this means, though, is that over here, if you have your expressibility as a function of pressure. You plug that in and you can solve it. If you have your expansivity, you put that in there and solve it as well. So the terms in this differential equation are measurable. And what it does essentially is it changes the game. So the game is really go out, measure a bunch of physical properties. The physical properties are then related to the derivatives in these differentials for our state functions. And the state function is volume, but the state function can also be free energy, can be enthalpy, the internal energy, whatever. There's lots of state functions, but they're all things that can be related to physically meaningful terms. Measuring them is not always easy, but that's a lot of what science has been for the past 100 years is mapping out what these values are. For the sake of finishing off, but we'll have a happy conclusion here about the single component ideal gas. We have a state function that looks like this. PV over NT is equal to CON as constant R is equal to 8.21 times 10 to the minus 2. That is liter atmosphere per Kelvin mole. So that's P is pressure, V is volume, T is temperature, and N is the number of mole. And this is our gas constant. So, continuing with our discussion, well, any questions about this? Hopefully it's more or less straightforward. I don't know what your prior education was. When I was an undergrad, thermodynamics was still very cryptic for me, even going through it. And it wasn't until grad school that someone pointed out that it's actually not that bad, and most of the things we're looking at are just measurements. And you've got some curve that some experimentalist measured and plug it in and integrate it. It's really handy. Well, let's finish up our discussion of definitions, and then we'll move on and talk about energy and enthalpy. So something we need to define is the definition of an intensive. Intensive variable, extensive, VL. So the intensive variable is independent of size. And this extensive is dependent on size. Talking about our ideal gas, you can imagine a system. Blue markers, I had it. You can imagine a system like this. Some T, T, V. It's a closed, isolated system. We call this state 1. And our state 2 roughly twice the size. V, or maybe a better way to do this is to think about it as no, I'm gonna do it this way. 2, 2, 2. Well, in principle, these, and put these in contact with the same, maybe they won't be isolated. 2 of these are the concept of the same universe. We can keep the temperatures the same. We can keep the pressures the same. Volumes, though, we have V to 1/2 of V2. So in this case, our V1 and V2 are extensive variables, and temperature, pressure are our intensive variables. And lastly, let's talk about the concept of equilibrium. We say something's in equilibrium if it doesn't evolve in time, if not. Time. So for example, got a system, it's an isolated system. I'm going to put an isolating wall in that system. I want to say that both sides have the same pressure, P constant, and T1 is not equal to T2. And you say, well, is this an equilibrium? Yes. It doesn't evolve in time. Now, you could say, well, I'll pull this wall out. You pull that wall out, then pressure, that doesn't change, but now temperature 1 to evolve. Final state E, E, T3. Now this final state is going to be an equilibrium as well. This equilibrium is global. There's nothing that you can do to the constraints, the walls or whatnot, that will change the system. This equilibrium, when we had the isolating wall, it was equilibrium, but it's a metastable equilibrium. So there's different types of equilibrium depending on if you can get your system trapped. We'll learn in terms of free energy that we're essentially looking at this. So here, maybe your global, and this is metastable. Metastable equilibrium is extremely important for material science because most of the world we work with is metastable, right? We like systems in which we have lots of metastable equilibriums, and we can choose the processing path we take to trap our system in a useful metastable equilibrium. We like it when we can control how easy it is to move. So there are some systems, for example, piezoelectric materials. Piezoelectric materials work because we have two equilibriums, and we're able to take the system and flop it back and forth between those two. We want to be able to control those, where it gets stuck, how much the system changes going from one metastable equilibrium to the next, and we want to be able to control the size of the energy barrier, or the free energy barrier, that has to be overcome. And one final comment is the concept of spontaneity. So when you remove this wall, this evolution is spontaneous. So if you have an isolated system and something occurs spontaneously, that means there's an increase in entropy. And we'll talk about that probably Wednesday, probably Wednesday next week. But I want to introduce just the concept of spontaneous. You can have two different states in an isolated system that are both in equilibrium, but in order to move from one to the next, there has to be some increase in entropy. So for example, talking about our ferroelectric materials, we might have two ground states, but those two states moving one to the next, if it's in an isolated system, nothing's going to happen. There has to be an external force. In this case, however, we don't have that because we pulled out that wall and everything spontaneously evolved, and once it's in that new ground state, it stays there. So, questions about any of this? Yeah.
If a material doesn't exhibit any metastable state that we know of, is it possible to predict one?
Through defects.
Okay.
I would say that, and this is also something important, most materials are extremely boring. It's the defects that make them useful. Being able to control dislocation, generation, the dislocation structures, pinning, etc. That's what allows us to control the mechanical properties. In the case of piezoelectric materials, in particular perovskites, which are kind of the workhorse of the piezoelectric world, what we're doing is we are introducing the old-fashioned ones, single stoichiometric compounds. We were introducing, we weren't actually doing much, we were just taking them off the shelf. The new ones, though, we are changing the composition, and by changing just slightly, 5-6%, we're able to tune what the barrier is, and we're also able to tune how far apart these states are, how large of a change they have. Okay, so let's start talking about energy and the first law of thermodynamics. Okay. So we'll start out with a system. And say it's going to be an isolated system. And we say that it starts out in state 1. And it moves, or it changes, to state 2. And then let's also define the internal energy as U. So this idea of internal energy, I don't like the term, and most of the time when we talk, we say energy, and it implicitly implies the energy of the system, which is the energy inside the system, is the internal energy. Your textbook likes it, a lot of thermodynamic textbooks like it because I say it's more of a traditional sense. That's the way it was talked about because people want to talk about how energy moved from, say, the universe into the system. So our variable U, oftentimes I'm just going to slip and say energy, but do know that it deals with internal energy. U also is not necessarily the only variable. In many textbooks, you'll also see E, but I'm going to be using U in this class. E has other implications, for example, electric field. So we're going to use U. So if we talk about this system, we say at state 1 it has energy U, and that changes to energy U2. Well, it's isolated, and by conservation of energy, U1 equals U2, so delta U equals 0. Well, we can change that, and we can change that by having some way that the system can interact with the universe. And the universe, you can think of it as a big reservoir. So let's take out that wall and put in a new one. And over here, we have the universe. Right? The universe, you can also think of it as a reservoir. Now, because we defined our walls, we can choose the way that the system interacts with the universe. So let's say that we've made a wall which is adiabatic. And by adiabatic, I mean only work and mass. So you think of that as, a perfectly insulating wall, so no heat can pass, and it's impermeable, so no particles or atoms can move back and forth, but it's flexible. So this wall can, for example, bow in or bow out to work. So talk about the work that goes into the system. We're going to do W for work. So now, if our system changes from state 1 to state 2, U2 minus U1 is equal to negative W. This, well, hang on, I need to define another term here. Before I write that up, let's say U1 is greater than U2, then this is equal to negative W. Our W is defined as the work done by system on the universe. So I do theory for a profession, and I find myself constantly making tiny mistakes. So one of the tricks that I do to make sure that I actually understand what's happening is I put in kind of bogus numbers. So I'm saying U1 is less than U2. So I'm going to say delta U is equal to, say, 3 minus 5 is equal to minus 2. So I can think of this then as, the system is losing energy, and I'm defining work as being done by the system on the universe. So maybe I should draw this backwards. Sorry, let's change the direction of that arrow. So work is done by the system on the universe. So the W arrow is always going out. And because the system loses energy, that's why we have this negative here. If you do theory for a living, anytime you have a mistake like that, you get caught. And it's not that you don't make mistakes as a theorist, it's that you find tons of little tricks to double check yourself. So the definition of work is work done by the system on the universe. The arrow for work is always pointing out, and that negative sign tells us about the energy being passed. Now, that's one system. We have another system we can have. I'll change colors and let's now talk about having a wall that's red, and the natural definition of red is heat, maybe. It is in this classroom because I only have a red pen. So Q, let's say that we have a system which is thermal only. So it's rigid and it's impermeable. So now, moving from state 1 to state 2, say if 2, so U equals U2 minus U1 equal to Q, where Q is the here. Heat into system. So again, you put in say 5 minus 3 equals 2. You stand as your sign check. And this is the definition of Q. And you could take and combine these if you wanted to. You could have, say, the reservoir system, another reservoir, you could have Q in and W out, or you can draw this single one, I guess. Say we have Q, you have say W out. And if you have this type of situation, then delta u, u2 minus u1 is equal to q minus w. Or in infinitesimal form, du is equal to u minus w. So this expression law of thermodynamics. So this internal energy is a state function. When you think about it, you got a system. If you can define all the relevant physical parameters that define it, this is the state, temperature, pressure, volume, if you're dealing with an ideal gas, many other variables if you are dealing with real materials. But it's the state variable. And the implications of this being a state variable the first is that the internal energy can be written as a function of our independent variables. The set pi it's a set of independent variables. The next implication is that we can write our internal energy in differential form, where du is equal to the partial of u with respect to independent variable 1, holding all variables to pn, or call it pi. Actually, I'm going to call it n. pn. Yeah. Pn constant. 1 n, so I'm going to say there's n variables. dp1 plus partial of u with respect to p2 holding p1, p3 through pn constant, dp2 plus plus the partial of u with respect to pn holding p1 through pn minus 1 constant, dpn. And then the third implication is that integrating from state 1 to state 2 of the internal energy is equal to integrating from state, right? Is equal to negative the integral from u2 to u1 du. We're saying that it doesn't matter the path, it only matters the initial and final conditions. So if you go from u1 to u2 and u2 to u1 by a different path, the only thing that matters are the endpoints. And this is
the most generic way to write what we were talking about before for the single component ideal gas. And the reason that I like writing it this way is because, at least for me, when I was a student, I found dealing with ideal gases made sense, but generalizing that didn't really make sense. So we'll talk a little bit about how this expands to other sources, and also talk about internal energy and how it applies to free electron gases. So, not free electron gases, but that's where my brain lives most of the time, to single component ideal gases. So, ideal gases, now we have U, P, V, and T, and we have delta U is equal to Q minus W. So let's talk about work. And work is everything a system can do not heat. Now, in the case of our single component ideal gas, that's pressure volume. In the case of real material systems, it has to do with stress, strain, PV. It has to do with stress, strain. It has to do with electric field, electric displacement. It has to do with magnetic field, magnetic field strength. So basically, when we take what we're learning here and we apply it to real material systems, for example, you have a part that's in tension, right? This is all going to be work, even compositional, changing the composition, right? So the chemical potential and number of components available. Everything's work, it is not heat. So this is okay. Now talking about heat. In the case of our ideal gas, this is going to be work equal to delta V is equal to V delta P plus P delta V. For the sake of simplicity, most of your textbooks, ours included, makes this assumption that delta P equals 0. So pressure is a constant. That's handy, and we're going to work with that here. The implication now is that W is equal to P delta V. We also have the U is equal to partial of U with respect to volume at constant temperature, dV plus du, the temperature at constant volume, dt. recruiting chair for MSC
What?
apparently. No, I am actually, but we're supposed to.
What did he ask? What class is
Column
this?
102.
I
Just said yes and had him sit down.
Forgot.
Wait a
You would have been so lost.
Oh god.
I don't even think you would know what these symbols mean.
Yeah, analog. Okay, so got 3 pages left of notes on this section. We'll do like one step forward and then we'll finish this up next week. So this is what we have. Let's say what if B P constant. They're both constant. Well, they're both constant. Then W equals delta V equals 0. No work. Which means that dq minus del q minus del w is equal to du is equal to this lazy. Just rewrite this over here. Is equal to dw minus q. If this is 0, we also have this is 0, which means that here that del q is equal to du is equal to du dt, a constant volume dt. So we're basically saying that the change in internal energy just has to do with the heat being passed, and that's related to this du by dt, and we'll talk about that next time. I should point out that oftentimes people use a notation V, so that is the flow of heat at constant V. Again, it's not a notation that I particularly like, but just be aware that you'll see that occasionally. And sometimes it'll slip into my notes as well, but a lot of times it's not, and it's just implied, for example, here. So any questions about what we covered in energy so far? Hopefully it's more or less clear. Yeah.
Changing it so it's a constant volume and changing pressure is just switching the variables around, right?
Yeah, thermos, once you get the basic ideas, and those ideas are actually definitions, for example, work done by the system of the universe, heat absorbed into the system, you get all the signs right, then the rest of it is just swapping around variables. Thermodynamics, very, very simple, a set of definitions and a bunch of bookkeeping. Which is a terrible way, but I mean, if you make it sound hard, then people think you're fancy because you're a theorist, but it's not hard. It's actually pretty simple. So Friday, I'm gonna have a video where I solve problems. I will send you the link to that, and I'll send you the link to this one as well after I get the sound edited, etc. And anything else we need to talk about?